Section 4.1, maximum and minimum values. Where we look is first on the interior of a function if you have a closed domain. And when you're looking at the interior, it's going to have a max if you see the top of some kind of a mountain. So locally, this is the top of a mountain. That's considered a local max. And then when you're identifying local max, you state the amount of the maximum. This one's, the scale is by halves. So this one has a local max of 3. For the minimums, you're looking for the bottom of a valley within the graph. I see a valley here, I see a valley here. So this graph technically has 2 local or relative interchangeable words, minimums. The first minimum occurs here at -2, and then the next minimum occurs here, which is at +2. The absolute maximum would be the highest or the lowest point on its given domain. In this particular example, the lowest point is right here, so that's the lowest on its given domain, and the value is -2, so it has an absolute minimum of -2. For the maximum on its given domain, that's the highest point, which is right here, so the absolute maximum is 4. Another word for absolute is global. Then endpoints can be considered maximums or minimums, as we just saw in the closed domain. So when you're looking at endpoints, just look just in the general area near the endpoint. If you are rising to an endpoint, that's considered a local maximum. So at this endpoint, I have a local maximum of -1 at x equaling -7, and another up here because I am rising until I come to the endpoint. So another local max of 4 at x equaling 1. Fermat's theorem. If you definitely have a maximum or a minimum and you know the derivative exists, then what does that derivative have to be? Well, we look here at where the derivative exists versus where it doesn't. So nice and smooth right here, the derivative exists. This is a corner or a cusp, corner cusp. Those, the derivative, don't exist. So visually, if this one exists and these don't, what are we saying then about that derivative? That derivative is equal to 0. I'll give you a moment. You should pause the video, read about the extreme value theorem. Then, for this particular example, how does it work? Well, you have to identify, like you did in other functions and other theorems, you have to identify continuity. So we say, since f of x is continuous, it's known that it's continuous, so I'm just stating it's continuous on its given domain. Then, by the extreme value theorem, otherwise known as EVT, f of x has to have a max and has to have a min. So in our case, the max was at x equaling 1, because it specifically wants the x values, and then the min was on -3 to 1. The minimum would be at x equals 1. I would take a moment, stop the video, read through the definition of a critical point, and then all those different types of critical points that are given, you want to take a look at those critical points. Oops, I just realized over here has a maximum at 1 and a minimum at -1. All right, so those critical points is when the derivative is 0 or doesn't exist. Another vocab that's not on this list that you want to kind of be aware of is when the curves go flat. So they're either always increasing or always decreasing, but have flattening points. Those points where the derivative is 0 are also referred to as a saddle point. What we're going to do now is work with some functions where we're going to find the critical values. To find critical values, it's all about slope. I take the derivative. In this case, I have 3x squared minus 3. Doing some factoring, 3 times x squared minus 1 The values where it's critical are at positive and negative 1. Well, what type are they? Since they did indeed make the derivative equal to 0, then the type of critical point that I have is a stationary point. So I'm going to say f of x has critical points, because we have to identify where those occur, at negative 1, 3, and 1, negative 1. To find these values, we're simply plugging the plus or minus 1 into the original f of x. And both are stationary, because they both make the derivative equal to 0. My next one, when I take the derivative, I get 5x to the 2/3 minus 6x to the negative 1/3. To simplify this to look for critical values, the factoring move that I'm going to do is I'm going to factor out a fractional exponent, and I would say the majority of time when you have the fractional exponents, it works out nicely if you factor out the lowest value. And the reason I'm saying that is because 5x to what power here makes a positive 2/3. This would have to be 3/3, which is the number 1. So I'm getting a linear factor by taking out that negative exponent, minus 6. This is really equal to 5x minus 6 over the cube root of x. Well, critical values are where you identify things having zeros. So we have critical values in two spots, and they are where the numerator goes to 0 and the denominator. So the numerator going to 0 is 6/5, and again, to find its height, you plug back into the original function. And the denominator going to 0 is critical. And then who is stationary? Well, I'm not going to set this equal to 0 because this equals 0, but this technically is undefined. So only 6/5 with negative 6.098 is considered stationary. The last one, I take the derivative, and I get negative 1 over x squared. So I might be tempted to say x equals 0 is a critical value. However, x equaling 0, when I look back in the original, I can't divide by 0, so this is not a critical point, because on the original, it was undefined. Finding the absolute maximum and the absolute minimum values of f on the given interval. Well, to find any kind of max or min, we take the derivative, so I'm going to say f prime of x, and this one involves the product rule. So I have the first one as is, derivative of the second, plus the second one as is times the derivative of the first. Doing some simplifying, I get it down to x e to the negative x minus e to the negative x. Factoring out that e to the negative x, we're left with x minus 1. Doing a quick rewrite to identify any critical values, we have this fraction. X equaling 1 is critical, makes the numerator 0. The denominator is exponential, it will never be negative. What I'm going to do now to identify absolute max and absolute min on a given interval is I'm going to look at the critical value and find out what's happening on the graph by analyzing the slope. Sorry about that. So there's my sign chart to analyze the signs on the derivative. If I go left of 1, going down to 0, plugging it into here, 0 minus 1 is negative, e to the 0 is positive. This region here is negative, which means my curve is decreasing. If I plug in 2, the other end, 2 minus 1 is positive, e squared is positive. So what happens with this thing is it starts at 0 at something, goes down, goes flat, reaching a minimum, and now before I go back up, I have to know where do I go up in relation to where I started. So I'm going to pause for a moment on that and do what we call a candidate's test. A A candidate's test, here it is in vocab, candidate's test identifies maxes and mins on a closed interval. What it does is it says you take the endpoints, any critical values, and you analyze their heights in comparison with the sign chart or standing alone. So if I plug 0 into the original, I get 0. If I plug 1 in, I get negative 1 over e. 2 is negative 2 over e squared. Well, I know this one is the absolute minimum because it's heading down and it's bottoming out to 0. I needed the comparison. So 0 is definitely higher than any negative number. So I'm going to stop my graph right here and say this is kind of a quick little visual as to what's going on with that function. So I'm going to say this one has an absolute max of 0 and an absolute min of negative 1 over e. For the next one, the trig function, we take its derivative. F prime is equal to cosine of x minus sine of x. Then I want to identify critical points. If I'm dealing with cosines and sines, I'm not going to have points of non-differentiability. Those are nice, smooth, continuous functions. So I'm going to say 0 equals cosine x minus sine x. And some of you right now could possibly identify the stationary point that exists on that given interval. If you don't see it, you can manipulate by moving a trig function to the other side, and maybe now you're saying, oh, I recognize what it is. If you still don't have it, dividing by cosine gets me tangent x equaling 1. So 3 different opportunities to say that critical value is pi over 4. Then if I do my velocity sign chart, or f prime, it's not velocity, it's not particle motion. So I have pi over 4 here. The low end is 0. So if I plug in 0 into the derivative here, cosine of 0 is a 1, minus sine at 0 is a 0. So this is positive. In general, if things are not double root, you're going to start to notice they're going to alternate, and they will alternate until they are not what we call a double root. That means you have a factor being squared. Or you could test your pi over 3. Then I do quick visual. I'm starting at 0. I'm heading up. So this is potentially the absolute max. I'm heading back down, but the question is, do I go down below the original level or not? So I'm going to do that candidates test again to see what's happening for values. I have 0, pi over 4, and then pi over 3. 0 goes with 1. Sine of 0 is 0. Cosine of 0 is a 1. Pi over 4 is 1 over root 2 plus 1 over root 2, or you could do root 2 over 2 plus root 2 over 2. Either way, they both condense to a root 2. The pi over 3 becomes the square root of 3 over 2, in for the sine, plus a half. If I add these together, root 3 is greater than 1. If I'm taking 1 plus something bigger than 1, I get more than 2. That means this sum is bigger than this. So that means the graph stops somewhere above my starting level. So in this case, I'm going to say an absolute max of the root 2, and the absolute min is back at the start at 1. For the next one, you want to start thinking your pre-calc skills to think about end behavior before we even start to analyze the graph. So I'm going to find critical numbers first, and I'll go back and talk about the end behavior in a moment. F prime of x is equal to, first, I'm going to take the derivative of the second one. By the chain rule, the derivative of the inside is a 1. Derivative of x is 1 times the second one as is. For this one, to get it into factored form, I don't want to expand these out. I want to realize this is a common factor. So I'm going to pull an x minus 2 squared. Now that is what we call that double root situation I was referring to before. We're left with 3x plus an x minus 2 from this one. Simplifying, I have x minus 2 squared times 4x minus 2. So the critical numbers, meaning when is the derivative, because this one will equal 0. There's no fraction. So the critical points I'm getting from here are stationary, and they are at 2 and at 1/2. So those are all the critical numbers of f. Now we want to identify, well, what's the local minimum value of function f? When I go to do the sign chart here for f prime of x, I have the 1/2 and I have the 2. The end behavior of this, that's going to come into play as well. It's a fourth degree polynomial, so that means even end behavior. It's leading positive, so that means it's going up, up. Let's see what happens below 1/2. If I plug 0 into the derivative, and I always plug into the most factored form. If I plug 0 in, this is squared. That will always be positive. So I only care about the critical values in here. 0 in here makes this piece go negative. If I plug in 1, that makes this piece go positive. If I plug in 3, this piece goes positive. Notice there is no sign change around 2 because this was the double root. So the charts will alternate unless you have a double root or an even degree root. The local minimum value, I'm decreasing until I get to 1/2 and then I increase. So that means I must have a local min at 1/2. If you plug 1/2 in, then you would end up getting negative 27/16 for the amount of the minimum. Find the local maximum. Well, we know its end behavior is up, up, so I start up. I am decreasing until I get to 1/2. Then I'm increasing. Now this tells me my derivative is going to 0, which means the graph has to flatten. So I'm going to flatten, but then I have to go back up. So I've created what's called a saddle point here. As I look at this graph, the saddle point is temporarily flattening. That's my minimum. There are no local maximums on f. Just like there's no absolute maximum because of the end behavior of up, up. The absolute minimum value, well, looking here between the derivative analysis and the end behavior, the absolute minimum is the same as the local minimum, which is negative 27/16. Pause the video and I would read number 14. I'm going to find the acceleration first because we're asking for the maximum value of acceleration. We get negative 3t squared plus 8t plus 2. To find the maximum value of anything, I would analyze the derivative of that function. My derivative is negative 6t plus 8. This is going to coincide with your pre-calc skills saying, oh, I should know that this thing has a maximum at the vertex of the parabola because it's an upside down parabola. But let's see how the calculus plays out. I get a critical value of 4/3. Then I'm going to analyze what's going on A prime because the slope identifies what's happening on the original function A. Well, to the left of 4/3, if I plug in 0, it's positive, which means A is increasing until it gets to 4/3. And if I plug in a number here after, say I plug in 10, that derivative is now negative. So that means this 4/3 is where the maximum occurs. The problem asks for the acceleration, the maximum value of the acceleration. So A at 4/3 is equal to 22/3. The last page, you want to grab your graphing calculator and type that function in. I would pause and work on setting up a window so that it will you'll be able to look at it nicely. All right, now that you're back, here we go. We have a sine function of x, and then close the parenthesis around the sine function, square it, divided by x, and then minus 1/3. Oops, I hit something else. Delete, delete, divided by 3. Okay. My window for this one is 0 to 2 pi. So I'm going to say 0 to 2 pi. And then I'm going to change my x scale so it's in terms of pi. So I'm going to say pi over 2. For the y values, now let's discuss. We're trying to find critical points. Well, critical points mean where the derivative is 0 or the derivative is undefined. Since I'm dealing with a sine function, I'm going to just focus my efforts on tiny numbers, because I want to see where am I crossing and look at the general behavior of the graph. And I'm seeing enough of it so I don't have to adjust my window again. It looks pretty close over here to the right, but I can see that it's definitely not hitting. So for my trig numbers, depending on the original function, I tend to stick with smaller numbers, and then if I have to adjust the window, I adjust it accordingly. I see that it's hitting 0 here and here, so that means we have 2 critical values on that given interval. So we know a function is continuous, and that function is the sine of x. According to the extreme value theorem, that's EVT, then what does f of x have? It has a maximum. It's guaranteed to have a maximum and a minimum. Since it's a sine curve, it has a maximum of 1. Now realize that it has that maximum in more than one spot, which is okay. It's just that it has a maximum and a minimum. And this sheet doesn't have the negative 2 pi to 2 pi, but we are looking on negative 2 pi to 2 pi. So, and a minimum of negative 1. Does f prime at 4 exist? Well, let's see. F prime of x is equaling 2/3 x minus 4 to the negative 1/3, which would look like, when I rewrite it, 2 over 3 times the cube root of x minus 4. That means when you plug in the 4, you're dividing by 0. F prime at 4 does not exist. And then I did change my problems here, so I'm going to do just this part B. Show that the only local extreme values of f of x occurs at the 4. Well, to show that your extreme value occurs at 4, we're analyzing the derivative. Is the original function increasing or decreasing? That's what the derivative will tell us. If I plug in left of 4, if I plug in 0, then this is a negative, and I can take the cube root of a negative number. If I plug in a 5, I get a positive. So that means function f is decreasing, then the derivative doesn't exist, and then it's increasing. Visually, what this one looks like, and you can double check by plotting the original into your calculator, decrease to increase, but it's like this kind of a scenario because that derivative doesn't exist at a corner point. So we're going to say the only local extrema, so the only local extreme value is a minimum at x equaling 4 because f prime of x goes from negative to positive at x equaling 4. Just so you know, in general, sign charts are not justifications for anything. You have to interpret your sign charts in order to get credit. So just keep that in mind. Sign charts are a very helpful tool, but they are not used as the work to justify anything.